Okay, hi, hello everybody. My name is David. I'm a software engineer at Meta. And before that, I worked at a bunch of different companies, mostly doing big data things, because I'm a big data geek. And today we're going to be talking a lot about big data. But this is not a big data conference, this is a software development conference. And so we're going to be talking about data tools from the perspective of software developers, like I'm guessing most of you here are. So let's do a quick check. Who here actually writes software for a living? Yeah, that's pretty much what I expected. Perfect. So we're in the right place. So what we're going to be talking about is what are the problems, different problems that we solve with data tools, how they evolved from 20, 30 years ago to what we're actually using today, and how, if we had to solve this problem right now in this room as software developers, how we would actually build these tools ourselves and see if it's actually close to what really exists in the industry. And generally just see what the different tools are and where you're likely to meet them in your day-to-day work, if at all. Right. And so before we start, we can talk about what is big data. And there's actually exactly 2 jokes you're allowed to tell about big data. The first, of course, is a picture of Lieutenant Data from Star Trek next to a slightly bigger picture of Lieutenant Data from Star Trek. Hilarious. And the other joke is a Facebook post by psychologist Dan Ariely from 2013, and he wrote that big data is like teenage sex, in that everybody thinks everybody else is doing it, everybody wants to be doing it, and no one's actually doing it right. And that was 10 years ago, and that was the peak hype for big data, and at the time that was very funny. The thing is, now is 10 years later, and most companies actually have a lot of data, and everybody's doing big data, so I stopped telling that joke. So we're stuck with the only one official data joke now. But really, big data is a field of actually dealing with large enough or complex enough amounts of data that it's actually hard to process them with traditional tools, meaning databases, relational databases like most of you I'm sure are familiar with. Let's do a quick check. Who has ever written a SQL query? Perfect, we're in the right place again. Good, I'm just verifying that we're going in the right direction. Okay, so like normal data tools are databases, the stuff you use every day in your applications, microservices, whatever. And at some point we get to a place where either there's just so much data we have to query and process that normal databases just don't cut it anymore, or the speed at which data comes in and we have to ingest it and do something with it is so high that, again, we can't just do that on a single instance, even the most expensive and biggest database we can buy. And at that point, we need to actually use specialized tools. But these aren't some magical tools that only big data people understand, right? All of those were written by software developers, like all of us here, to solve a specific problem which wasn't solvable until that, right? And this is a cycle that happens in software development very often, right? A new problem shows up that you have to solve in an engineering way, and it's usually a combination of economics and some different trends in the industry which change the way you use data. So for example, the early 2000s were a really good example of this. We had the internet and search engines. Then a few years later, we had social media, and a lot of people started generating just tons of data all the time. And the economics of it, combined with the fact that storage got way cheaper, generated a whole new generation of completely new tools which solve problems that you couldn't actually solve before that. Right? And so when we talk about problems and economics, we need to think about what is the value of data, right? And this is a slide which I really like. It's from an article written by Scott Yar, the CTO of VaultDB, a long time ago. And he talks about the fact that the value of data isn't constant. Right? The value of data changes over time. And it's important to see what kind of data we're talking about. When we look at an individual item of data, right? So one record or one row in a database, one event, usually the value of this event starts very high, close to the moment when it was generated. The best example would be, for example, we're working on an e-commerce website, and our item of data is a user's shopping cart. So while we're browsing the website and the user does stuff and updates the shopping cart, that object is very valuable. If we lose it, we lose the customer. It's going to be very upsetting. But once the user checked out and used the shopping cart, and we log that in a database, the value of that data item goes down very quickly. 5 months later, no one actually cares about this one record in a database. However, the value of data in aggregate, right? So lots of historical data. For example, all of the shopping carts for the past 6 months. The value of data in aggregate starts out usually very low because looking at statistics of shopping carts for the past 5 minutes isn't very informative, right? But if you look at all the shopping carts for the past 6 months, suddenly that data in aggregate becomes very valuable because you can generate trends, you can get statistics, analytics, and business intelligence, and you can train machine learning models and all kinds of stuff with this data because we now have enough of it and it goes back long enough, right? And so there are different tools to address each one of the sides of the slide. There are specific tools, usually the ones you normally use in your daily work, which are on the left side of the slide, which is tools that are very good at dealing with small amounts of individual records. You know those as normal everyday databases, right? Your SQL Server, your PostgreSQL, whatever they are. And they're optimized to be very good at dealing with a small number of records very quickly. And we don't really try to store very many of those. And if we try to do aggregative operations with those databases, they kind of work, but they're not really optimized for that. On the other side of the slide, right, when we deal with a lot of data and we want to store a lot of it for a long time, and then we want to get value out of it by aggregating and getting insights or running analytical queries on it, we have a completely different set of tools to deal with those, because normal databases aren't actually very good at dealing with queries that touch a lot of data all at once, right? And so this brings us to the idea of OLTP versus OLAP databases. OLTP stands for Online Transaction Processing Databases. These are the databases most of you know every day, SQL Server, Oracle, whatever. OLAP stands for Online Analytical Processing Data. And those are specific tools that are optimized not for individual operations on records, but rather on analytical operations, which means a lot of data or a long history of data going back. And those have to be optimized very differently, and they have very different economic implications, because it's okay to pay a lot of money for a database which brings a lot of value out of all of your data, and it's usually not as efficient to pay a lot of money for a database which just stores some data for a few hours or a few weeks. So when we think about what we do with analytical data, let's look at a query, right? This query, I wrote 1,000 versions of this kind of query. I'm sure most of you did too, when you were looking at some data and trying to figure stuff out, right? This is a very typical analytical query of data. You select some data, you aggregate it, you count, you average, you max, min, whatever. Then you join a few tables together because you want to touch a lot of data. You subselect for some conditions, and then you group and you sort and do all kinds of stuff, right? When you look at this query, it looks very simple. I'll give you a sec to look at it while I take a sip. And the thing is, this query has a lot of different engineering problems hidden behind it. So we'll go through them. There's at least 4 really big, very incompatible problems going on all at once in this analytical query, which is just an example. Most analytical queries kind of have all those problems in them. One is aggregation, right? The first one, aggregating data is very expensive computationally and in terms of I/O, right? Because unlike pulling out one record from a database, if you want to go and you want to have the sum of all the sales transactions in your entire table of data for 6 months, there are very few ways to do this efficiently. You have to read all the data, or you have to read it in advance, generate indexes, and that's also very expensive. So this is a big engineering problem. Joining data sets is an incredibly difficult engineering challenge. It's especially hard in distributed systems, where some of your data is on one machine and some of the data is on another machine, and you have to bring one side of it to the other. So that's very expensive and very difficult to do. And we spent the last 50 years optimizing databases to do joins efficiently. And we're still not done. Actually finding data within a data set, so your where conditions and subselects and subqueries, that's a separate engineering issue where you need to prepare your data in advance to be queried, build indexes, maintain them. And finally, grouping is a completely separate engineering issue where especially in a distributed system, in order to group data together, you have to shuffle it between different machines over the network, which is both very slow because you have to go over the network and also very complicated to actually coordinate. And so each one of these issues is a completely separate branch of development. And most tools can't really solve all of them all at once. And so over time, we've built different big data technologies which address a few of these issues really well and kind of ignore the others because they're optimized to do something really well. So we'll take a look at the first example, and I'll start with a story. Let's say it's 1980, and we're in a big company, IBM, something. And at the time, databases were not just a piece of software you install on a machine, right? It's a big closet appliance that you buy from some company for $500,000. You install it in a data center, and you have very few people who can access it. And it has a proprietary interface and its own data format. And a big enough company has a few of those. And they're not necessarily all from the same company, and they're definitely not interoperable because none of the database vendors actually want to cooperate with other database vendors. And your business analysts come to you and say, we want to take the data that's in the sales database and do a report that uses data from the user database, which are in actually different cities and owned by different teams. How do we do this? An equivalent problem would actually be today, right? If you did your best architecture, you embraced microservices, and your architect is very happy because each microservice has its own database, and you have your users microservice, and you have your sales microservice, and your inventory microservice, and now the BI people come to you and say, well, we want to do a report across users and sales and inventory. How do we do this? Like, they're in different databases. And it's the same problem because you actually cannot do an efficient join across multiple data sources, multiple databases. And in order to actually solve this problem, the new idea came about in the early 1980s, and it's still very popular today, which is a data warehouse. And the idea is very simple. We can't really efficiently join data and use data across multiple data sources. Let's just copy all of this data to one place, call it just a normal database, but we'll not let anyone use it in production, because what happens if you let analysts run queries on your production database? Oh, thank you. Yes, it's going to be very bad. Oh, by the way, just as a disclaimer, I'm going to be asking questions, and they're not rhetorical questions. When I ask a question, my honest hope is that somebody will actually answer it. So don't be polite, right? I don't need to give this disclaimer in other countries. The further south you go, the less polite people get. And so people just answer me, sometimes without me asking anything. But you people are exceedingly polite, so when I ask something, I'm seriously asking a question. They're not trick questions. They're relatively straightforward, so please be brave. So yeah, what happens if you let analysts run queries on your production database? It lags, it can be overloaded, it's going to compete for resources with day-to-day online queries. And so we just copy all this data into a separate database. We'll call it the data warehouse, because that's where we store all the data forever. And we're going to keep a long history of data in that data warehouse. All of our data is going to be replicated and copied into one place. We can run join queries on it. We don't need to compete with the production use cases, so we can run very long queries without affecting users. And it's going to be wonderful. Of course, you can't just copy data easily, right? You have to build some tools that allow you to extract data from one database and copy them to another continuously. And that's a process called ETL, extract, transform, and load. And over the past 50 years, we've built, I don't know, 1 million different ways to do that. But overall, this idea, which is very old, is actually still in use today. So the first place where the idea actually appeared is a research paper by Devlin and Murphy from 1899, which just explains the idea of a business data warehouse. And this was just revolutionary at the time. No one has apparently thought that it's a good idea to take all of your data, put it in one place, and then let analysts actually use it, right? And this is something that you can still find today. If you go out to cloud providers, you'll find Redshift in AWS, and there's a BigQuery in Google, and I can't remember the name of the thing in Azure, but every cloud provider has their own data warehouse, or you can buy a very expensive proprietary data warehouse. But ultimately, they're all the biggest benefit of having a data warehouse is it gives you normal relational database semantics. So you have your schema, you have your relational data, you have queries in the same language in SQL, which is very convenient because everybody speaks SQL. But it's optimized not to work on individual records. It's optimized to actually run analytical queries a long time. But it's not optimized to run many queries side by side, unlike an OLTP database, which is optimized to run a lot of queries all at once. And so this is very convenient and very flexible, but there are a couple of problems with it. Queries just take a long time, because when you run an analytical queries on your past 6 months of data, you have to go and actually physically touch 6 months worth of data in terms of I/O and disk bandwidth and network bandwidth and all that stuff. And people are not very patient, especially business people who want to get answers. And so a different way of thinking about solving some of the challenges in this analytical queries showed up a few years later after the idea of data warehouses. And to explain this, I'm going to take another sip, and I'll tell you a story. So imagine you're a software developer. Should be very easy. And one day, your CEO or some product manager comes to you and says, we have this table with 6 months worth of sales transactions. And I want you to build me an application which, when I click a button, shows me the total number of transactions, like a big dollar amount on the screen. And I want it to be really fast. I don't want to wait. I've used your data warehouse, and it's too slow. So go do whatever it is you do in the background with your software stuff, but build me an application which, when I click a button, immediately shows me the result of the last 6 months of sales. And we'll say we'll do it, we'll round it to the nearest day, right? So we'll define a day as midnight to midnight. And I know some of you are thinking midnight in which time zone, because you're smart asses, and we're going to ignore that. So what do? I'm seriously asking. Hopefully somebody will say, okay, what would you suggest we do to solve this issue? You can build any kind of software in any language, use any hardware, whatever you want. You just need to make one thing, one button, you click it, you get the result of total number of sales. Scheduler is a good direction. What does the scheduler do?
Runs it when he's not at work, so it's ready when he presses the button.
Perfect. That's a really good answer, and aggregate, perfect. Both those answers together are pretty much what actually exists. So what we do is, in advance, because we only need to press the button once before when the manager comes to work, right? We actually do the query in the background when everyone's asleep, and we store the number. The query is very simple. The result is just one float number. It's like 8 to 16 bytes maybe, depending on which language and which year this is happening in. Right? And so you store it in your memory, and you click it, and you show the number. Perfect. And everyone's happy. You put this in production, and a week later, the same manager comes to you and says, software development person, that was really good. Remember when I said I just need the one number? So I lied. Here's some scope creep. I want you to actually do this, not just one number, but separately for every country in the world. You think. OK, well, that shouldn't be hard. There's like 200 or so countries without getting political. OK, no problem. What do we do to show the same number, but for every country in the world? Yes, both of you are very correct. While you're doing this count, you also group it by the name of the country, for example. And instead of storing a counter in the memory, you store a hash table, right? And the key of the hash table is the country, and the value is obviously how many sales were in that country. And you keep the old counter, goes right out. You also have the total number. Perfect. It takes you a while to write this, and everybody is happy. And then a week later, the lying manager comes to you and says, haha, scope creep. And he goes, OK, I want this by country, and I want this by month. And I also want this by day of the week and by category of product. Can you do that? It's obviously very easy, right? It's not a big deal. And so it goes on and goes on. And essentially what you're now building is a multi-dimensional data structure in memory, which every dimension is one of these categories. So one dimension is how many counters are in the country, per country, how many sales are per product category, per day of the week, and so on and so on. And so what we've actually built is an OLAP cube, which is a multi-dimensional data structure that holds aggregate results for every possible slicing and dicing of the analytical query. And we run this in advance, because the thing we want to solve is the biggest problem of data warehouses, which is queries are just very slow. And this idea was published in 1993 by Edgar Codd and C. Sally. I can't remember what the C stands for. But Edgar Codd, just as a sidetrack, is a well-known data scientist. Edgar Codd, about 20 years before this, wrote the 12 rules for relational database management. This was in the late 70s, early 90s. OK, so quick story time, right? Before the 1980s, databases were just Wild West. There were no relational databases. There was no standards, no SQL querying, nothing like that. Every company had their own database, and it did its own completely different thing. And then towards the late 70s, query languages became a thing, and then the newest, hypiest thing was relational database management, which is you build your tables and schemas, and you define foreign keys to have relationships between tables. And that was a revolutionary idea at the time. And then every database vendor who wanted to sell their software slapped a very thin layer of relationality on their non-relational database, called it a relational database, and sold it. Because that's what vendors do. I used to work for a database vendor. We're not, never mind. And so Edgar Codd, who was a purist in terms of databases, was very angry with this essentially disingenuous way of using the word relational database. And he wrote a manifesto talking about the 12 rules for what makes a relational database. And that's still followed today. If you go and you look at Postgres and MySQL and SQL Server and all of those are actually relational databases according to the 12 rules of database management. So the same Edgar Codd, a few years later, was working for a company called Arbor Software, and they created, first of all, published this research paper explaining what an OLAP user analytics is and how the cube works. And they built something called Arbor Essex, which stands for Extended Spreadsheet Software. Essentially, it was a multi-dimensional Excel spreadsheet. Everyone can imagine an Excel spreadsheet in 2D. Now imagine that in 5 dimensions. If you can, congratulations. But it looks kind of something like this. Obviously, I'm limited to 3 dimensions plus time, so that's what I have. But if you can imagine a tesseract or a hypercube, or further dimensions above that, then that's the idea of the OLAP cube. And you can slice this multi-dimensional data structure across any dimension and get the intermediate results of that dimension. So if you slice it by year, as the example here, we'll get all the results for year 2004. And if we slice it by category along this axis, we'll get all the results for every year for this category of product. And this is an amazing optimization on data warehouses because it actually gives us the query very quickly. There's obviously a problem. Can anyone spot the problem?
Well, at some point it starts to get slower as well.
That's, first of all, always true for every kind of software. But in this case also, yes, you're exactly right. What happens if we have dimensions with very high cardinality, which means there are very many unique values of that dimension? Imagine, for example, one of the dimensions is the user ID, and there's, let's say, 3 billion users, like in Facebook. What happens to the cube? Yeah, because the number of data points you have to store is the product, the multiplication of the cardinality of every dimension. So if you have very high cardinality dimensions, the cube becomes extremely inefficient. It becomes not an optimization, but actually much worse than just using a data warehouse. Right? And so this solution is actually very efficient, but for a very narrow set of use cases where you have low cardinality dimensions, and I think some of you missed it, you have to declare your dimensions in advance because you have to pre-compute those. You can't just change your mind and write a different query because the data doesn't exist yet. In late 97-ish, I was working at Intel, straight out of college, and we had an OLAP cube. It was a Microsoft OLAP cube server, which, by the way, wasn't a Microsoft product. They bought a company called Panorama Software a year before, took their software and slapped Microsoft label on it. And we would build this cube overnight. It took about 6 hours to build the whole cube, and then in the morning we would come and discover whether it actually worked. And half the time it did, and half the time it didn't. And so every day we would go and see if the cube building succeeded. If not, that was an entire day gone. And if it did, wonderful, we didn't have to do anything. So that's 2 ways of solving some of the challenges of these analytical queries. Now, those are very interesting, but there's a problem that's very common to both of those. And that is the fact that dark data exists. Now, what is dark data? Some of you might have jumped to dark web, and no, it's not data about drugs and guns. Dark data is data which is written but never ever used. And there are many studies which look into how much dark data actually exists. And depending who you believe, somewhere between 50 and 90% of all data ever stored isn't actually used to provide any value. Nobody actually queries it. Now, intuitively, I'll give you an example which makes it very clear. Think about application logs, right? Every application has logs. How often do you go and read all of the logs of all the applications in your production, whatever it is?
Never.
Sometimes it's extremely useful. Something breaks, you have to go and you have to find a specific subset of logs for a specific time or specific service. Most of the logs are never actually used. Most logs are actually dark data. This is true for almost every category of data. It's especially true for machine-generated data. So sensors, logs, all kinds of stuff, right? The problem is you still want to run analytics on data that includes a lot of dark data. And what happens when you take all this data and you put it in this very expensive piece of software and hardware called the data warehouse or an OLAP cube? First of all, you pay a lot upfront, right? Because you have to pre-process the data and compute the cube and ingest the data. So you actually have to pay a very high cost in terms of resources upfront to even put the data in. And then, because it's an online piece of software, the database has to continue working. You keep paying maintenance on it all the time, even if nobody is actually querying it. So actually, it's very expensive to store data in OLAP-type solutions in data warehouses, even if no one's actually using them. So what can we do? We can take another sip of water and think about this. So let me ask you a leading question. What is the cheapest and most effective way to store a bunch of data? Sorry, say again? Compressing is good, but you're way ahead of us, sir. You're very advanced. Before you even compress it. File. Who said file? You put it in a file. Yes, perfect. That's the easiest and cheapest and best way to store data. You don't put it in a database, which is very expensive. You just slap all of it into a file in a raw format, and files are, that's what they exist. A file system is really the best database for just a bunch of data. So you put your data in a file, and you pay very little upfront, because writing data directly to a file in a raw format is very cheap. And at least these days, storing data is relatively cheap as well, right? Storing data is, I don't know, if you go to AWS, a terabyte of storage costs $20-ish per month, right? Which is, like, my laptop has like 2 terabytes of data on it. So storing data is not very expensive, and the cheapest way to do that is just pour all of your data ingested in a raw format into a file. Of course, that brings us to a problem. Why did we spend the last 40 years building databases and optimizing stuff if we're just going to put stuff in a file? How do we actually run the query on the data? And that brings us to data lakes. So the idea of a data lake is to separate 2 parts of traditional database software. Like every database, you can think of it as 2 separate pieces of software. One is the storage layer, right, that manages the software and the data on disk, the data format, how it's actually written, builds indexes. And the second part is the compute, which is what executes the query, reads the indexes, reads the data, and gives you the result. And in almost every database software, they're part of the same application. They're the same piece of software. But what if we could actually split those apart? And we move the storage to the cheapest form possible, which is just plain files, and we change the compute part of the database to understand files and read them directly. So we flip the economics of the database upside down. And until the early 2000s, this wasn't actually very economical, which is why it never happened before that. We had files for a long time, right? But nobody actually used files as a database or a database system. And what changed in the early 2000s were 2 things. One, search engines were invented because the internet became big enough to require storing a lot of data, right? So in the early 2000s, we passed something like 1 billion web pages on the internet. And this is just around the time of the last round of search engine wars. Is anyone old enough to remember search engine wars besides Google? Yes. Yahoo, AltaVista, all of those, yeah. So search engines were a classic example of something that has a bunch of dark data. You ingest all of these URLs, you index them, and most of the time nobody searches for the web page that you built for a cat, right? Everybody wants a small subset of web pages. And so this idea of let's put everything in files, and we will pay very little upfront. We pay very little in terms of maintenance and storage because storing files is cheap, because storage got much cheaper in the 2000s. But we'll pay a much higher cost when you actually want to use the data, right? So why do we pay a much higher cost? I'll give you an exercise. This is the most classic example of big data problems. Every big data course has this as the first example. It's called word count. Imagine you have a 1 terabyte file of text, plain English text. And I come to you and I say, build an application which tells me how many words are in the file. How do you do that? Perfect. That's the perfect answer. You open the file, you read it sequentially, and you count the change from white space to non-white space or whatever it is, depending on how complex you want to make it. But ultimately, there's really only one way to do this, and there are very few ways to optimize this for runtime, right? Because you have to read every byte, because if you miss any of the bytes, they could be a white space or not a white space, and you would miscount. So you read every byte, and you actually get a result at the end of it. And before we go into scaling out, is there any ways to optimize this for runtime? Yes. I mean, okay, depending on the business, but generally, yes. Sorry, just like one. Oh, chunk the file up, okay, and then?
Wait, 1 megabyte at a time.
It's a good direction, and you were? Okay, yes, so that's always the first thing people think of. It makes perfect sense. The problem is, especially if we're talking 20 years ago, we're using spinning disks. It's actually not very efficient to try and parallelize data reads from a hard drive because you're limited by the reads, the sequentiality of the read head, and the bandwidth, right? So even under the most ideal conditions, right, the most bandwidth for reading you can get from a hard drive is about 150 megabytes per second. With an SSD, you can get to 300, maybe 500 megabytes per second. But if you have to read a terabyte of data, your limiting factor is always going to be I/O bandwidth, right? There is no way around this. And so the only way to solve the problem is just not solve it. The only way to solve this problem is to just split this file into a bunch of different hardwares, different machines, and run part of the problem on each one of them. So obviously, you still pay as much in total bandwidth and total CPU power, and actually there's some extra overhead. But because we're only optimizing for runtime, we don't really care as much about resources, this is really the only practical optimization you can do for runtime. You just parallelize it to different hardware. Because the combined bandwidth of 1,000 hard drives is 1,000 times 150 megabytes per second, right? And it is usually more than enough compute, more than enough CPU and memory on each of those hardwares to do the task. So the problem is mostly bandwidth. Now this is the core idea behind the data lake. Instead of bringing the data to where your compute lives, you take your application, the one you talked about, we write the application, and we copy a copy of this application to every one of our machines where the data lives, and we run it locally. We bring the compute to the data instead of the other way around. Because usually the problem is the bandwidth of the data and not the amount of compute we have. Right? And this idea was revolutionary in the early 2000s, and a whole giant range of technologies came out from just this idea. And it came about right around 2004, 2003, that Google published two of their most famous white papers. The first was the white paper about the Google file system, which is a distributed file system, super efficient, very resilient. It stores multiple copies of every file across a network of machines. And it allows us to actually do the thing we said, which is the first part of the solution, right? Which is take a file and spread it across a lot of machines. And the second white paper talks about a new algorithm at the time called MapReduce, which is the algorithm that Google used to do precisely the thing we just invented 5 minutes ago, which is take our application, send a copy of our application to every machine in the network, run it locally on a subset of data, bring all the results back, and combine them together. Those are the map and reduce steps, right? You send the application out, you map your data, and you get the intermediate result, and then you reduce the intermediate results into the final result, right? And this idea is just amazing because it solves two of the biggest problems that data warehouses and OLAPs had, which is it's very expensive to scale them, whereas if you have 1,000 very cheap machines with consumer-grade drives, in combination, they are much cheaper than a $500,000 data warehouse from IBM. And that caught on. Hadoop is the name of the first open source system that implemented this idea outside of Google. The two engineers who actually wrote Hadoop were trying to solve something that's very interesting. They were trying to build a search engine which could index 1 billion pages, which today doesn't sound like a lot. 1 billion of anything isn't really that much today in terms of data. But in 2002, indexing 1 billion web pages was considered pretty much impossible in terms of economics. right? Because they did a research and they found that to index 1 billion web pages for a search engine, they would need a system that costs roughly $500,000 upfront and around $50,000 maintenance every month, which is not something you can afford as a startup who wants to build a search engine. And so they took the ideas from these two of Google's white papers, and they built a system called Hadoop. And today you wouldn't run into Hadoop anymore unless you work for like a very, very conservative bank. But there are different systems that take the same ideas and move it forward. And Hadoop caught on. The problem is, as it often happens with new technologies, the first generation of a solution to a problem that was considered impossible before that is usually written by software developers for software developers, which means it's incredibly inconvenient to use for normal people. You can think of it as, there's plenty of examples, but in this case, Hadoop required you to write a Java application using some APIs, compile it into a jar, and then use a very complicated configuration system to spread this jar across a network of machines, run it on a local file system, bring back the results, and the results would be written to a different file on a different file system, and then you have to go and read the text file. And that was your API for the data processing system. No GUI, no SQL queries, nothing like that. Now, the second generation of those tools, as always happens with technology, was optimized for non-software developers. So they had a nice query language like SQL, and they had a GUI, and all kinds of nice things. And today, we're actually going towards the third generation of these kind of tools. And usually the third generation is actually not even an improvement on the technology, but rather a change in mindset where instead of, let's think of it this way, the second generation of every software is usually much more complicated and much better, but it requires a certain set of skills which few people have, and it creates like a new mini profession. It happened when databases, relational databases came around and DBAs were invented. It happened when DevOps became a thing and DevOps people were invented and became like a big profession. And it happened around 2010 or so when data engineering became a profession because it was complicated and important enough to have like a separate mini profession just for that. And usually what ends up happening is a few years later, companies get sick of hiring all these very expensive engineers. And what they want is for one company, like Amazon, like Microsoft, like Google, to hire all of these smart people and build something that's easy to use for everybody else. And this is more or less what's happening now. All of the big data tools are now transforming to platforms, usually by big cloud providers or big vendors. And normal people like us can go and just swipe your credit card and use the platform because they have a nice UI and a nice query language, and we don't need to maintain a very expensive infrastructure on the back end. Right? And this is where we're going towards like the third generation of data tools. But going back to the story, remember the file we were reading? So I lied when I say there are very few ways to optimize reading the file. There's actually a lot of ways to optimize it, but you have to ignore all the things I had said before that. So around 2010 or so, when people were trying to solve how to optimize reading files efficiently, because that's the cheapest way to store data, they decided that it may be okay to pay a little bit upfront, to do a little bit of pre-processing, to optimize the way that we store data in files in order to make it easier to query. We're not going to go full database, right? We're not going to build a whole different kind of database here. We're not going to reinvent indexes and memory caches and all that. But it's okay to do a little bit of work upfront to make the brute force queries afterwards slightly more efficient. And this is why columnar formats were invented. Now, what's a columnar format? Let's go back to another example. Let's say that instead of saving raw text in a file, we're allowed to change the data before we store it in the file. How can we optimize the word count example we had earlier to make it easier and more efficient to count all the words in the file? The only query we're ever going to do is count all the words in the file. How can we change the application that writes the file to make it easy to count the words? Exactly, that's an excellent way to do it. As we write the words, we count them, and we just store the count, I don't know, at the end of the file, at the start of the file, some header, and then we don't even need to read the file. Right? We solved the biggest problem. We don't need to use any bandwidth or any I/O. We just read the header, we get the count. Now, we need to get, in the real world, it needs to be slightly more complicated, because we don't just need to count it, right? We need to build a lot of different statistics and read them in advance and write them in advance. And then we might not need to read the entire file because we can read much less of it and answer the same question. And this is what columnar formats actually do. The problem with this, of course, is if you're going to do pre-processing, you cannot just directly write all of the data to the file as it arrives. You need to buffer some data, pre-compute it, right? Because in order to count it, you have to buffer some of it, count it, and then write everything you buffered. So columnar formats, and there's actually two standard formats today in the industry. One is called optimized row columnar format, or ORC, and the other is Parquet, depending on your pronunciation. And they both more or less work similarly. The way they work is, when you're writing to the file, instead of spilling the data directly into the file, we buffer, by default, about 10,000 rows. And on those 10,000 rows, 10,000 records of data in memory, we compute statistics on every field, on every column. And we compute, for example, for numeric columns, we'll find the minimum and the maximum, and the average, and the sum, and count, and pretty much all the statistics. And for string columns, we might build a Bloom filter or a dictionary of unique values. And once we've done that, we write the records into the file, but we don't just write them like we would in a database. So the way you write to a database is every record is sequential, because normal databases deal with individual records. And the most efficient way to read the whole record is read it sequentially. So in a standard database like SQL Server, every data record in a table is written as a sequence of bytes in the file. In a columnar format, we flip that around. We take the values for one column and write all of the values for the column sequentially. Then we go to the next column and write that column sequentially. The next one, the next one, the next one. And then we close the row, the stripe, as it's called, and write the footer, which has the statistics for every column. And the reason we do that is, going back again to the difference between OLAP and OLTP databases. In normal databases, we usually want to get the whole record or update the whole record. In analytical applications, we usually want to run aggregations. And it's very rare when you need to aggregate every single column in your data. Like if your data has 50 different fields, you're not going to group by every single field of those 50, right? You will usually do something like select whatever, name and count by 3 fields or 2 fields or something. And so it's very rare when you need to read all of the data, but it's very, very often that you need to read all the values for one column. And so it makes the most sense to write all the values sequentially for that one column, and then the next one and the next. And so if we go back to the example of word count, how would we write a word count over a columnar format? We wouldn't even count anything. We would go to the index of the file, find how many stripes there are, go to the start of the stripe, find the footer at the end of the stripe, read the statistics for that one column, which gives us the count, go to the next stripe, go to the next stripe, sum all the counts, and that's our answer. We would need to read maybe a kilobyte, maybe 2 kilobytes of data, and it doesn't even matter how big the file is, because you only read the actual statistics that are stored. And this bypasses the entire problem of bandwidth. And you can also obviously do this very, very easily across a cluster of machines, because each one of those will do this individually on the local files, then give you the result, and we can sum the results from every different machine in the cluster into one combined result. So all this stuff was actually invented by multiple different companies over the course of very few years, roughly from 2010 to 2012. And there are many reasons for that, but mainly are, again, economics and changes in the way people behave. 2010 and 2012 is roughly when social media became, unfortunately, a part of all of our daily lives. I say unfortunately, even while I'm working at Facebook. But it's Facebook and whatever it was before, MySpace and media and all the stuff that moved online became big enough that it required all of these companies, so Google and Microsoft and Facebook and a bunch of others, to write their own version of these big data tools, and they all work very similarly. All the ideas we talked about, columnar formats, writing and reading directly from files, separating storage from compute, each one of them implemented a tool that does exactly the same thing with some variations. They're optimized for slightly different things, but it's surprising how many companies invented basically the same thing. And again, for reasons for economics and solving a problem which wasn't actually solvable until then. Now, of course, as with everything we looked at, data lakes have one big problem. And the problem is, you write the data directly, which means it doesn't really have a schema. You can write any kind of data. And over time, data lakes, which is just the repository of all the data you have in your organization as just a collection of files, usually turns into a data swamp, which is an official term. This is like the equivalent, this is the data equivalent of spaghetti code, right? Code goes from code to spaghetti code, data goes from a lake to a swamp. Which means no one actually knows what's in the data lake. There's like a bunch of files. No one is brave enough to delete those because they might be useful. And over time, you just get more and more of it. And you forget what the format is. And the file itself doesn't really have a schema. It's not like a normal database where you have a table with fields and rows and all that. And that's a big downside of data lakes. And that's a big upside for data warehouses and OLAPs, which is why they still exist today, right? Because if the data lake was so superior, everybody would just switch to that and abandon data warehouses and all the other technologies. But the fact is they didn't, because there are big advantages to actually structured and schematized data. It's much easier to work with it. And usually the people who pay the bills, which is the business people, listen to the analysts, and analysts are lazy, and they want it to be easy to work with data. I hope there aren't any business analysts here. I apologize in advance. And so, as usually happens when we solve a problem in very different ways, optimizing for different directions, eventually the different implementations start borrowing features from the other. If you think of it, it happened with different front-end frameworks. Over time, different front-end frameworks kind of borrowed features from each other. Different data technologies also borrow features from each other. So modern implementations of data lakes usually steal a lot of the ideas, a lot of the benefits from data warehouses and the other way around, which brings us to this idea of a data lake house, which is a data lake that works like a data warehouse. It's a stupid name, I hate it. But the idea behind it is actually very interesting, which is if we give up, if we pay a lot of complexity, because usually when you have a hybrid technology, you always pay with increased complexity. But if we're okay with having much more complicated systems, we can have the benefit of both the data warehouse, which is structured data semantics, which works kind of like a normal database, and also the very cheap storage of a data lake. And obviously, it's something that not every company will create for itself, because again, the level of complexity is exponentially higher. But enough companies wanted this ability to go and work with data easily, but also not pay too much money for it. And so in the last 3 or 4 years, this idea of a data lakehouse became very prevalent in the industry. And the way it's usually implemented is you wouldn't normally build a data lakehouse on your own in a company. A few companies like Facebook, like Google or Amazon have enough engineers and enough interest to build their own data lakehouse. Most normal companies would just use it as a service because we're in the 3rd generation of data technologies, and it's much more advantageous to actually buy this as a service from a company like Snowflake or Databricks. There's a bunch of them. I'm not selling any of those. And just use that as a service instead of building your own data lakehouse, which is actually just combining a bunch of open source technologies in very complicated ways. And the advantage is, it's still not clear which is better, right? If you want just using something very simple where you can go and use a tool like Redshift on AWS or build your own data warehouse, you will get the advantage of having structured data. You will have asset semantics, which is a database term for behaving like what you expect from a database, for being having atomicity and having consistent data and having isolation between data operations and being durable, which is something you expect in a normal relational database, and data warehouses work the same way. Data lakes behave like files. They're not consistent. There's no protection for durability. If somebody is modifying a file while you're reading it, it's probably going to cause data corruption. And they're generally slower because, again, they're files. You're paying a brute force query over all of the files, and it will take longer. And they have no schema, so you have to actually validate the data while you're reading it, which means you have to spend a lot more effort in making sure the data is clean and validating it and so on. But it's really, really cheap. And it's very flexible because you can write any data before you know how you're planning to query it, which is a big downside of OLAPs and data warehouses, where you have to declare the schema and create your cubes up front. You actually have to know what you're going to do with the data before you store any of the data. With data warehouses, it's very attractive to companies who like to accumulate data, and all companies like to accumulate data, which is they can store everything and figure out how to query it later. And a Lakehouse is kind of like a hybridized version of both. It's supposed to give you both. And it's supposed to, and there's a big asterisk because like every good engineering question, it starts with, it depends how you use it. And maybe it's going to be more expensive because if you use a Lakehouse as a service, usually the services are priced by usage and by storage. So you store more data, you pay more, you query it more often, you pay more. And it kind of becomes a trap eventually. Right. So before we finish, I want to talk a little bit about the future, right, and give you like a little glimpse into what I think is going to happen. And this is purely my opinion. There's no research behind this, mostly just experience. And there's a couple of spoilers I want to talk about. The first is what's probably going to happen for software developers in terms of using data. And the bigger trend that's going to happen, I think, in the next 3 to 5 years is something that's called a data mesh architecture, which is this idea of instead of having data be a sub-profession for a very specialized group of people, data engineers, build data platforms which are self-service, which would move the ability to control data and manipulate it from specialized groups like a data platform architecture team. Every company these days has like a data infrastructure team or a data engineering team or one of those. And those are the people who own the data because they're the only ones who can manipulate and use these complicated tools. And over time, we're going to see, I think, a shift in data ownership from specialized teams to normal software development teams. This kind of thing happened in the last 10 years in different domains as well. A lot of companies now started building teams that have all of the different sub-professions in them. So you'd have a front-end engineer and back-end engineers and a DevOps person and a quality or automation engineer, all in the same team, and a product manager, so they can actually build their own domain services on their own and not depend on anybody. And data is still the only exception that I very often see, which is you'll have all of these people in one team and a separate data team. I think enough companies are going to recognize that it makes more sense to move data ownership into the normal integrated teams as well, which means they're going to start using self-service tools to actually give control of data, creating tables, moving data around over to software developers, where really that actually belongs. And this is one of the bigger trends I think is going to happen. The other is what I call biggish data. And this is not my term. I stole it from a good friend of mine. So if you remember at the start of the talk, we defined what is big data, which is working with data sets that are too complex or too large to be dealt with traditional tools. And the thing is, what was big data 20 years ago and what was big data 10 years ago is very different from what's considered big data today. Because traditional tools didn't just go to sleep for 20 years. SQL Server and Postgres and Microsoft or SQL Server and Oracle, they had 20 years of advancement and progress. So the standard tools we have today are so much better at dealing with a lot of data and doing a lot of this work quickly than they were 20 years ago when big data was essentially invented. And so the mindset of a lot of companies is lagging behind what actually exists today. What normally happens is companies overestimate how quickly they're going to accumulate data. Some overly excited architect, like myself, will go and say, we're going to start a new project, and we're going to advance, and we're going to be prepared for hypergrowth. Our data is going to grow exponentially because our clients are going to grow exponentially. And we need to build a data lake, and we need a data warehouse, and we need a lakehouse, and we need all these 7 other things before we actually experience hypergrowth. because when we do, it's actually going to be too late. It's too hard to add those things. And they overestimate just how much data tooling they need, where in reality, most companies have very linear and gradual growth in terms of how much data they have and how much their data needs evolve. And today, especially with cloud tools, it's very easy to fulfill most companies' needs with just relational databases and normal tooling. So how many people know what an exabyte is? Exabyte? Anybody want to say what it is?
A lot.
Yes, it's a shitload of data. But how much exactly? It's 1,024, if you want to be exact, petabytes. And which is 1 million terabytes, it's 1 billion gigabytes, 1 trillion megabytes, and so on. Right? So there are a few companies which actually have an exabyte of data. Facebook is one company, Google, Amazon, maybe Microsoft. There are a few companies which actually have an exabyte of data. Obviously, don't query it all at once. Much more companies have petabyte-sized data, right? The company I worked at before I came to Facebook had several petabytes of data. There are quite a few companies like that. But in reality, the vast majority of companies are in the terabyte scale. Tens of terabytes. Most normal companies don't actually go into a petabyte range. And a terabyte is actually something I can do on my laptop, right? So I can actually put a terabyte of data. At home, I have, I think, maybe 10 terabytes of storage across all my computers. Most people here have at least like a few hundred gigabytes on their phone alone, right? So a terabyte of data is not that much anymore. You can put a terabyte of data into pretty much any database that exists today. You can query it, right? You don't put it on your production database and run analytical queries on it. But it's okay to actually think of terabytes as not really very big data, right? The technology has moved on. So what is big data today is not what it was 20 years ago, and we don't actually need to run to big data tools to solve data problems. Most people in this room, if I ask you to go build me a data system which can handle 1 terabyte of data and query it, you can just spin up a SQL server or whatever it's going to be and use normal tools. There's actually a really cool database called DuckDB, duck like the bird. If you're interested, you should Google it. It's one of the new OLAP databases. It's an in-memory database which is designed to work on a single machine and do what used to be big data applications just on your laptop, right? It can read data from cloud providers. You can load data from S3 or from GitHub or from any web address or from locally, and it will load data into memory and run OLAP queries, analytical queries, in real time, very quickly, at speeds and performance levels which were just completely impossible 10 years ago. And so today, if you just want to build an analytical application, you can download something like DuckDB or a similar database on your laptop, put your terabyte of data here, and just run queries on it. And it will actually work. All right. So if you have any questions, we have 1 minute and 30 seconds. Otherwise, I'll be out in the hall, and I'm happy to chat about data wherever you want. And if not, thank you very much.